everybody. Anybody can confirm that you can hear my voice correctly?
We do.
Okay, and you can see my screen also?
Yes, now.
Okay, perfect. Thanks. So, my task today is to provide you an introduction about multi-body dynamics, which is the technology we will use with Adams. And together we will perform a full design of a satellite, or the solar deployment panel of a satellite. And you will be also invited to make an homework to complete this course. This introduction is an overview regarding the technology and some case study in order to show which is the origin of the code, which is the target of the code, and the evolution of the software. And it is only an overview. For sure, we have no time to see every feature and to make all the more advanced solutions, but could be a basic, for sure a basic introduction, but could be interesting for understanding the how the industry use this simulation tool for their design. So, if you have questions, doubts, curiosity, or something is not clear, please interrupt me. Probably I cannot see you directly, so please, professor can call me or stop me, or we can have a session question and answer at the end of the presentation. So let me start with the multi-body definition. What is a multi-body system? It's a mechanism defined by rigid and flexible bodies. In order to define a rigid bodies, an analyst has to provide location of the body in the space, providing 3 coordinates, x, y, z usually, providing orientation of the body in the space. And in this case, you have a sequence of angles in order to uniquely orient the object in the space. And you have to characterize the body with inertia data: mass, inertia, center of mass position, center of mass orientation. This is enough for the tool to describe the rigid body. The code, using your data, writes for you 6 differential equations for every degree of freedom of a body in order to describe, to analyze, to evaluate the position, velocity, acceleration of the body in the space, when the body moves, when the body is forced by some forces or torque, etc. If you define a flexible body, for sure the modelization is much more complete and complex. You have also to add information for defining the formation of the body. And in this case, you have a different level of description. You can have a linear description using modal method. You can have a nonlinear description. And in this case, you need to use a structural analysis in co-simulation with a multi-body code. From this, my first introduction, you can understand that the geometrical representation of the body in a preliminary design, it is not useful, is useless. You don't need to describe a graphical representation of your body, or better, you don't need to spend time in order to make a wonderful geometrical and graphical representation, because at the beginning of your design you don't know anything about your design, so you have no idea about the shape of the final shape of your body. So at the beginning we use simplified geometric representation, which helps us to visualize the system, but we don't need to use complex geometric representation. When you are in an advanced stage of your design, for sure, you can replace preliminary geometric representation with advanced geometric representation, importing data from a 3D modeler like CATIA, Unigraphics, PTC, SolidWorks, or other tool like this. When you use flexible bodies, in this case, you need to have a good geometric representation because the structural results depends from the shape of the body. The shape of the body will become important when you will have contact problem or interference problem or assembly problem in which the interferences, the clearance between geometries becomes important. But again, at the beginning of your design, we will use simplified geometric representation. The second group of objects to define a mechanism are the connections. How the bodies are connected each other using revolute joints, which allows a perfect rotation around an axis, or a translational joint, which allows a perfect translational movement between bodies, or a spherical joint, which allows 3 rotation, or a planar joint, which allows 2 displacement and 1 rotation, etc., etc. These joints are ideal because they are described by algebraic equations, so you cannot violate the equation, and the system cannot move or can found a locked position if you try to destroy the joint. The algebraic equation cannot be violated. In the real mechanism, you don't have an ideal connection, but a connection always has some kind of compliances. In this case, you have to define an elastic joint, a flexible connection using stiffness, damping, friction data. Depending on your purposes, your model can start with rigid bodies and ideal joints, and you can run a kinematic analysis or preliminary dynamic analysis. Then probably you can introduce flexible connection, and you can visualize vibrations, problem of the deviation from trajectory or something like this. And ultimately, you can substitute the rigid body with the flexible one in order to have the more realistic representation of a mechanism. When you have defined the topology of the model, you can apply to this model any kind of force you are able to describe physically and mathematically. So you need to know the physics of your problem, and you need to know how to describe it in terms of aerodynamic forces or elastic forces, electromagnetic forces, contact forces, friction forces, etc. In this case, the code adds equation to the system, and your task is to populate this equation with parameters. For example, an aerodynamic forces depends from speed, depends on surface, depends on angle, depends on density, etc., etc. If you don't have this parameter, or you don't have the function of variation of this data, like density depending on the altitude or angle of attack depending on configuration of the aircraft, is possible to evaluate the aerodynamic forces. So you need to know the physics, but you need also to know how to define these parameters. At the end of this, you have a mechanism able to move in a 3D space with no any limitation. So you can simulate the full flight of an aircraft from runway, takeoff, cruise, approach to the airport, landing, and run away again. Or you can also simulate the full circuit lap of a car, or a full movement of a robot, of a machine tool, or any other mechanism you want to simulate. At the end of this, due to the fact that you have rigid and flexible bodies, differential equation and elastic equation, you have algebraic equation or elastic equation for joints, you have any kind of forces for equation for the forces, your system is defined by a very, very complex number of equations, and you need to solve it using numerical solution. The numerical solution is performed by specific integrators, and these integrators are able to capture, to predict the behavior of a system before to create it physically. So the target of a simulation is to run thousands of analyses in the virtual world before to create the physical prototype. And as you will see, this is a great help for the designer, for the engineers, for the industry, for the researcher, etc. The code was created during the mission Apollo in the 60 years, so more than 50 years ago, but the first commercial release was developed in the 70 years, so 50 years ago. From 1973 till 1991, there was no any graphic user interface. So we created the model, writing a text file in which we include the data for the rigid bodies, for the joints, for the forces, etc., etc., etc. This file containing this data was sent to the solver, and the solver solve these equations and provide you output of the analysis. When you need in the past to modify something, you have to edit this file and change manually the data of your model, and you can understand that the activity was long, and in some case was boring, in some case was impossible in order to because you have many bodies, joints, etc. In 1991 was developed and proposed to the user the graphical user interface. It is called Adams View, and this is the interface. In this interface, you have specific feature in order to create rigid bodies using simplified or complex geometry, importing these from CAD. You can define flexible bodies, importing data from finite element code. You can use library of joints. You can use library of forces, of motion, of different elements like string, spline, variables, matrices, curve, array, etc., etc. So interactively, you can create the model graphically and numerically, and you can have this model in a parametric way. So changing, for example, a position of a point, the model updates automatically. Changing the length of a cylinder, the model updates automatically. Modifying the type of a joint, the model updates automatically. So the effort for the user is reduced, and we were able to expand the features and capability of the code, introducing a control system for mechatronic analysis, flexible body for structural multi-body analysis, acoustics feature for acoustic analysis, fatigue features for fatigue analysis, etc., etc. So the multi-body code now is a sort of integration tool in which you can perform not only multi-body simulation, but multidiscipline and multi-physics simulation. When you perform an analysis, you can ask the code to provide you measures in terms of position, velocity, acceleration, reaction forces, energy, power, deformation, stresses, noise, fatigue life, etc., etc. Depending on the purposes of your project, of your design, you can ask any information to the code. You run in this way the analysis, and in the same environment, you can visualize the results, diagrams, plots, curve, table, report, and using the graphic representation, you can visualize also an animation of the movement of your mechanism, and in this way you have the quantitative results to evaluate, and also you can also appreciate a qualitative prediction of the behavior of your system. So the Adams view environment is an environment in which you can model, preprocessor, solver, and post-processor, all the measures, all the results. So you have a full environment. From this environment, you can also run mechatronic analysis, structural analysis, acoustic analysis, etc., etc., etc. What you can simulate? More or less, there is no limitation, depending on the knowledge you have, depending on the data you have in your hands, depending on the purposes you want to achieve. For example, you can simulate the movement of a tractor with the trucks running on a hill made with sand or stones. The difficulty of this simulation is not the definition of the track, which is a combination of bodies connected by elastic joints, moved by wheels, tensioned by other elements, etc. The difficulty here is the definition of the road, which is not a typical road, but it is a soft road. The shape, the characteristic of this road change continuously because the truck modify it during the movement. So you need to have an algorithm able to simulate the behavior of the stones, of the sand, of a soft soil. The same for this characterization. If you want to simulate the behavior of a train, you need to know how to model the contact between the wheels and the track. And the contact is dominated by friction, by geometrical representation of the wheel and the track, from Hertzian law for vertical contact. You need to know how to model the air spring and the dampers, etc., etc. And in this case, if you want to release a payload in the space, you need to simulate the launching step of the launcher, the orbiting orbital movement of the satellite. You need to simulate the clearance problems. You have to simulate the flexibility of the shield, etc. And in this case, you need to simulate the behavior of an helicopter on a ship. And I want to emphasize this example. Let me use an activity I performed for a customer. In this case, we have this kind of problem. You have an helicopter approaching the carrier ship. You are on an open sea, so you are in an open environment. The ship is moving on the sea, so it is not a fixed ground like for a helicopter operating on Earth. So you have to consider that the landing activity is much more complex with respect to the activity of an helicopter operating on Earth. You have the impact between the movement of the helicopter and the movement of the ship. So the landing gears of this kind of helicopter must be more robust. And you have to redesign it, changing shock absorbers, changing tires, changing distribution of mass, inertia, structural effect. So you have to redesign also the fuselage, probably. You have to redesign the command line, etc., etc. So now we have the multi-body model of the helicopter, the multi-body of the sea, of the ship, sorry. You have the movement of the sea. But we have also winds. And the wind can aerodynamic forces. And the aerodynamic forces must be simulated considering variation in time and variation in space, because you have obstacles. So you have deviation of the flow of the wind. When the helicopter is on the carrier ship, the pilot ramp down the engine and the helicopter rotor start to slow down, and you can have an unlucky situation in which a combination aeroelastic effect between the aerodynamic forces and structural characteristics of the blade push the rotor to move in an abnormal way in the outside of the rotor plane. So you have a excitation of a flapping movement, and in this case, this helicopter cannot fly anymore, because probably in the blade you have cracks, and no any pilot will want to fly on a damaged helicopter. So you have to remove this helicopter from the flight line, with a great problem for the customer. So you have to consider multi-body model, CFD model, finite element model of the blade. This is a typical multidisciplinary problem in which Adams is the master. In this multi-body model, you add structural characteristics of the blade. In this multi-body model, you add aerodynamic forces evaluated by experimental test, numerical test, etc. You can also simulate any kind of condition, considering different motion of the sea, considering different characteristics of the rotor. The rotor is moving, the rotor is not moving, the helicopter is landing, the helicopter is on the ship, etc., etc. You can have different forces, and you have a very complex number of simulation to evaluate. And this is a typical problem, but it's not the only one, because you have also to make the helicopter in a safety condition when the helicopter is landed. For example, using a combination of cables. This is called the mooring, and my task is to evaluate how many cables I need, where are the cables, and which is the tension of every cable, in order to avoid a situation like this. You have the helicopter on the ship in any condition. So remember that you are on the sea. If you have an helicopter flying and the helicopter has to land, or you have an helicopter on the deck, you cannot stop or you cannot go back. You have to be sure that the helicopter can stay on the deck. You have a crew around the helicopter, so the helicopter must you have to avoid any damage, any problem. And considering rotary movement or not, considering different pressure of the tires, considering different position of the helicopter on the ship, considering different wind condition, considering different structural condition, etc., 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 you can understand that we have more or less 100,000 different configuration of your helicopter. And the authority want to have an answer for every of this configuration. And you cannot stay on the sea for 100 years to simulate, to make all this analysis, to make all these physical tests. So the industry perform thousands and thousands and thousands of analyses in the virtual world using validated simulation model, and the validation requires years of usage of the code and years of knowledge and experience on the simulation. You cannot perform an analysis after 1 day or 1 hour using the code. You need years to become expert, and with this kind of simulation you can predict the best configuration of every parameter in your model. You deliver the result of your project, you create the prototype, and you go on the OpenSea to make 2, 3, 4 tests, which are the final test of your design. You cannot use today physical test to see if something is going wrong. It is you waste a lot of time, money, and high level of risk. And if you follow some important design project in aeronautic industry, there are some projects that started 30 or 40 years ago, and this is because they need to make a lot of tests. And remember, this number of years can become double, 80 years, if you use only physical tests. And there are no a budget available to satisfy this request. So also for example, the F-35 aircraft, we make thousands of analysis. Also for NH90, we made a lot of tests. Also for Airbus and Boeing commercial aircraft, we use the code for make this test. Not only Adams, okay, but a combination of all the disciplines. And this is a typical trend in the industry. Before we run a lot of tests in the virtual world, after we had achieved a good or a optimized configuration, we start creating the physical prototype. The final target is to reduce the number of these physical tests, and in some industries, like automotive industries today, the prototype, the physical prototype, is very, very close to the final delivery of the design. And this was achieved using, in a very smart way, the simulation tool. In the 40 years ago, the average time of design for a car was 5 years. Today is 2 years. And this reduction of time was obtained using massively simulation, massively and in the smart way. Again, you cannot think that the code is a button to push. You must become expert in numerical simulation. You must become expert in the physical representation, in mathematical representation of the physical, of the physics, and you need also to know how to use the preprocessor, postprocessor, and how to evaluate results. Again, let me go to the next slide. You can simulate other models like motorbike, robot, packaging, washing machine, or general machinery equipment. So there is no limitation in this case. The limitation is only in our knowledge. Okay, so if you are able to describe the human body in multi-body environment, you can add the pilot on a motorbike. You can define the track, you can define the contact in the packaging system, you can describe the cables, you can describe aeroelasticity effect in the wind energy tower, etc., etc. So when we started, as I told you before, everything started during the mission of Apollo mission. Was evident in that period that you cannot use only physical tests to design the rocket and to design the lander and to design all the equipment to be used in the space, because you have to use this equipment in the space, and in the lab on Earth you cannot reproduce perfectly the condition in the space. There is no, on the Earth you have gravity. In the lab on the Earth you have no movement on the orbital on the orbit. So you have to simulate a lot your system, and they started using a structural code, thermal code, fluidodynamic code, and multi-body code. And year after year, this simulation tool became more and more powerful and important. And the first industry which understood the importance of the simulation was, again, the automotive industry. Also because in the industry in which there was a lot of money, especially in the past. So they spend time for becoming expert in simulation, and today, every day they run thousands of analyses in the simulation environment. The simulation tool evolved also in the importance because the computer become more and more powerful. So we have a laptop on our desk able to perform a very complex simulation. In the past, we need a supercomputer to do it. So in this way, we reduce the cost, the time to market, and the risk connected to the design. We can introduce innovation because we can test with no risk new things, new materials, new features, new movement, new situation. We have parametric models, so we can run optimization, we can run design of experiment analysis, we can use machine learning algorithm. And Adams today Adams has 50 years of development, so it is used from thousands of users in the world. The code is so famous and validated and accepted by the community that if you want to reproduce and investigate an accident, an aircraft accident, rail accident, or crash of a car, we use Adams to recreate it, and the results are used in the process, in the discussion, in order to understand the reason of the crash, of the accident, and to find the solution to avoid in the future the same situation. The goal of a simulation is to verify and simulate an idea of a mechanism, to find the better configuration of your parameters, to predict the behavior of a system before to create it. Today, in some industry, the usage of the code is so advanced that the simulation is used to validate your model, and in some situations you don't need a physical test. Imagine the advantage for the industry. Again, you have to demonstrate you are able to predict correctly the behavior, and to do it we made a lot of numerical experimental correlation. So again, we don't invent anything. We spend a lot of our time in order to improve our knowledge in the usage of the code. As I told you before, today the code is used for integration of different disciplines. So you can add avionics to your aircraft, you can add aerodynamic forces to your aircraft, you can simulate actuators, hydraulic, pneumatic, electric actuator, you can run analysis, and you can export loads for stress and fatigue evaluation. You can simulate analysis, you can simulate the mechanism to evaluate the noise of your system. So this is a typical interface called integration platform, in which you can manipulate many different data from different disciplines, integrate them in a unique model containing all this data, and using all this data and exporting results to some other tools in order to visualize, for example, the fatigue life of a component. This is another example, again, on a helicopter industry. This is a typical example of process in a durability environment. So this helicopter can fly in a 3D space. To fly an helicopter, you have to change the so-called collective pitch or cyclic pitch of an helicopter. The collective pitch allows you to move the helicopter vertically or to fly in a hovering, so in a steady state on a vertical position. If you modify the cycle pitch of the helicopter, you can fly longitudinally, laterally, okay, in every direction. The pilot has some bar, sticks, pedals to control the helicopter. His commands are transmitted to the helicopter rotor through the command line. We have links, arms, hydraulic circuit, electric circuit, contacts, etc., etc. So we have a very complex kinematic model. And when the command is transmitted to the swash plate, this element is called the swash plate. This element can be moved vertically, or can rotate, or can be tilted in order to change the angle of attack of every blade. So this element, the rotating swash plate, is one of the most important components in this kinematic chain, and you need to focus your attention on this component. Why? Because if you have some problems in this component is damaged and you have a failure, and if the swash plate doesn't work, your helicopter cannot fly, so the helicopter falls down. And you have to avoid this situation. You cannot have a crash of your helicopter. So this is a typical maneuver, combination of maneuver. Here you have 3 movies, but only for visualization. This is only one model. So during any a dynamic analysis, in the multi-body analysis, you have aerodynamic forces acting on the blade, and the aerodynamic forces are transmitted through links through the swash plate. You have inertial forces, for example, the centrifugal forces acting on the swash plate. You have the command of the pilot acting on the swash plate. And you consider the random combination of all these forces. And you have to simulate all of this situation. And if this body is not rigid, and it cannot be considered rigid, you can see some region in which during every flight, so during time, not in a specific configuration, but during the full flight, you can investigate and find that you have some critical situation. The red region in this flexible body, in the multi-body system, a region in which you can have a high level condition of stress. And this region must be investigated, because you can find a crack here, and if you continue to fly, the crack propagates and you have a failure of the helicopter. So, which is the typical process in the company? After the preliminary design, in which you decide the dimension of the swash plate, the material you want to use, the type of the connection, the volume occupied by the system, the weight of the system, etc., etc., etc. So after this entry design, you can start defining geometrically your system. So you can use a CAD model in which the designer starts to provide a preliminary definition of the geometry and the assembly of the system. From this preliminary definition, this element, this component, is transferred to the finite element user. The structural guy is able to perform all the structural evaluation, and it can export the flexible body for Adams. This model is a flexible body included in a full multi-body model, and I perform hundreds of different situation analysis. So I run this analysis, I collect results, I manage the results using a fatigue tool able to find the stress condition, fatigue life prediction, etc., etc. And if my object doesn't satisfy the requirements of the project, I can go back to the designer, asking him to change something, for example, to make more smooth a region in which there are a sharp representation, or I can decide to increase the thickness somewhere and reduce the thickness in other region. So he redesign the shape of the wash plate, transfer this new geometry to the structural guy, which recreate the flexible body for Adams. I substitute the preliminary model, the first model, with the second one. I repeat my analysis. I manage results, and this process is a virtual, full, multidisciplinary process in which I can optimize my model without create any physical prototype. This process can be repeated hundreds of times if I need, in 1 week, in 2 weeks, in 1 month of my design. When I am ready, I can go to create the first physical prototype. It means that I spend money for creating the physical prototype, because I have to buy material, I have to stamp, to manufacture the model, I have to assemble it in the real world, I have to put this physical model on actuators in the lab, I have to switch on the actuators, and I have to wait months of loading actuation in order to reproduce the full life of an helicopter. And if my process of design is good, with one physical test, I can validate my model. Imagine if you use only physical test. If after 3 months of physical test, your swash plate is damaged, you have to restart from scratch. And which is the reason of the problem? Who knows? You have to investigate a lot. And you spend other months for this investigation. And you have to spend other months to recreate another physical test, and other months to run again a physical test. This was an activity they performed 50, 60 years ago, not today. So today we use the virtual process before the physical test. This is a typical process in the automotive industry, in the aerospace industry, in some advanced general machinery industry. It is not a typical process there is not the culture of simulation in many industries, but this is the trend, and everything was, let me say, driven by the automotive industry. We have other examples like this. Let me show you an example in aircraft. So here we have a flap. The flap can be extracted and retracted from the wing. You know that the flap is the so-called high lift device. So it is a mobile surface. The pilot moves and change the configuration in order to increase the surface invested by wind and the angle of attack of the flap. Because during the landing and the takeoff, the speed of the aircraft is low, and you have to compensate this velocity with the surface and angle of attack to have the same force. Otherwise, the aircraft cannot fly. During this movement of extraction and retraction, the aerodynamic force changes continuously, and the flap is a flexible body. So you have to investigate a typical dynamic plus structural plus aerodynamics plus controlled system. Again, a multidisciplinary problem driven by multi-body analysis. And you can simulate also the failure of the actuators. So you can see if only one actuator is able to push and pull the flap, or you have to stop your flight because something is going wrong. And you can investigate any condition from zero extraction to the full extraction continuously. You don't focus your attention only on 1, 2, or 3 configuration. And it is very important in the aircraft industry. Let me show you an example on this, also for showing the evolution of the usage of the tool. This is activity performed for Leonardo aircraft in the past called Alenia Aermacchi. We want to describe the simulation of the so-called rejected takeoff simulation. So when you must stop your aircraft before to fly. Okay, this is a very specific situation, complex to simulate, but principally a high level of risk in the test. Before to simulate this, we need to see how today we can simulate it. It was a long process, a long journey. We started in the modelization of the C-27J transport aircraft of Alenia Aermacchi. And this activity was performed, started more than 20 years ago, in order to evaluate the performances in landing, takeoff, and runaway of the aircraft, because they need to certify, to make a certification of the model. This is the aircraft, and this is the journey. We started in this year, and for 5 years, the engineers of Alenia Aermacchi used the code to make preliminary landing gear and aircraft model. They need 5 years of usage of the technology to become expert in the technology, to become expert in the tools, and to make a validated numerical model. It was not a matter of 1 day, 1 week, 1 month. We need a lot of time to dominate all the physics involved in an aircraft design. In this period, we spend time principally on the landing gear. Then after this period, from 2001 to 2008, we improve the model, introducing, for example, the fuselage with flexible characteristics. And we simulate a lot of situations correlating and validating the numerical model with experimental data. And more recently, we were able to perform the simulation of rejected takeoff. So we started from simplified, from geometrical point of view, only from geometrical point of view of the landing gear, the main landing gear and the nose landing gear. When I say only geometrical simplification, it means that for tires, for joints, for shock absorber, for damping, for friction, for hydraulic element, we used very advanced representation in terms of function, algorithm, and data. So we had tire data considering a typical tire with a specific size, with specific inflation pressure, with specific curve of vertical force due to the variation of radius of the tire, or longitudinal force due to the longitudinal slip, lateral force due to the lateral slip, etc., etc. So we had numerical and mathematical representation of the tire. And the same for the shock absorber. We use curves like this, algorithm, function, hydraulic mechanism, pneumatic mechanism, etc., etc. So we have a very advanced representation of shock absorber and tires. We perform many simulations and we got very interesting results in terms, for example, of static attitude of the aircraft. If you are not able to find the static configuration of the aircraft, it's completely useless. You go ahead because you are not able to make this, let me say, simple analysis. And this static analysis is defined by characteristic of the main and the nose landing gear, distribution of the load in the aircraft, and we have many different loads of the aircraft, because you have an aircraft in which we have this weight or this weight, with different weight for every body. And the different weight means different position of the center of mass of the aircraft. And the position of the center of mass, you know, is important to make the aircraft stable or unstable. So we need to find a static configuration, and we correlate results. The second, and there are many other analyses of this. Then we introduce the flexibility of the landing gear. Here you don't see the structural model because for confidential reason I cannot show you the real geometry, but instead of a rigid body, this is a flexible body. You see only a beam, but it is not a beam. It's only a simplification in terms of visualization, again, for confidentiality purposes. But this was a flexible body. And with a flexible body, we repeat all the analysis in terms of the drop test, in terms of takeoff, in terms of landing. And we compare the drop test from a numerical point of view with the drop test made in laboratory. And we perform many situations considering the drop height, the wheel spin, the presence of friction, the characteristic of the plate, the total weight of the landing gear, etc., etc. This is a typical animation, but you don't focus your attention on the animation. This is typical results. And we compare numerical data with experimental data. And you can appreciate that we got very good representation from numerical point of view. And we repeat this analysis many times. Every time you change something, we repeat the analysis, okay? So we validate the landing gear. And this was performed when? In the first 5-10 years of the usage of the code in the company. Then we introduced the flexibility of the fuselage, starting with the sticky model, preliminary representation, beam model, and then with the full structural model of the fuselage. We perform a dynamic analysis, we saw results, we compare results in different conditions, we saw some discrepancy, we improve the model in order to reduce the discrepancy, etc., etc. And at the end, we validate also the model in the dynamic simulation, and we were able to see the reason of discrepancy, and we were able to improve again the model and to understand where the numerical model is different, why the numerical model is different, and if numerical results are valid or not. So we improve the model introducing different installation, changing something in the power, changing weight, blah, blah, blah. So we expand the analysis. We make simulation on uneven road, because you know that this aircraft can land on road that are not perfectly flat, because they are working in a dangerous condition. And now we want to make the rejected takeoff simulation. What is this analysis? You have to move on the road, and you have to accelerate. But if something goes wrong, before to achieve the V1 speed, you have to use different equipment like brakes, like air brakes, mobile surface, like thrust reversers, in order to stop the aircraft. If you go over V1, you have to take off and to go back to the landing. And if something is wrong, like a problem in the flap or the aileron, it's not good to fly, okay? If you are not able to simulate all these different conditions, you can have this kind of problem. If you are using only brakes, you can have the damage of the landing gear. So what we did, we started using different aircraft configuration. We use different situation in terms of brake pressure, brake application. So with brutal application, smooth application, we use the air brake. So using the mobile surface, we activate the thrust reverser, etc., etc. So at the end, we perform a lot of analysis, and the number of analysis is more than 1,000. Simulating all different conditions in order to find which is the best combination of brake, thrust reverse, and anti-skid braking system, etc., etc., in order to make the rejected takeoff maneuver safe and to validate our project. Okay, this is another typical situation. But this is not enough. If today you want to perform a co-simulation between Adams and the CFD code, now you can use advanced technique in order to transfer movement of the aircraft to the CFD code. You change the aerodynamic field because the landing gear is moving in the aerodynamic flow. The center of pressure of the forces change, and these forces are transferred back to Adams in one analysis only, using Hello, can you hear me?
We do now, Daniele.
When you lost me?
Well, basically 10 seconds ago.
Okay, sorry. So let me jump to the last two examples. What you can do in the aircraft environment is possible also in the space industry. This is a very famous movie called 7 Minutes of Terror. This movie is in YouTube, and you see in this movie Adams' model of the rover and the lander for the Mars missions. This is a movie created by NASA, the Jet Propulsion Laboratory. They use Adams from many years in order to design the landers and the rover, like Spirit, Opportunity, Curiosity, and last year, Perseverance. The reason of the usage of simulation is that a spatial mission is one-shot mission. You have no another possibility. Or works or fail, no other possibility. And the mission is difficult, not only because you have to consider the trajectory of descent, you have to consider the deployment of parachute, the opening of the shield, the extraction of the landing gear of the rover, the heat shield separation, the rover separation, touchdown, etc., etc. You have to consider that this maneuver is performed millions of kilometers from Earth, and you need 7 minutes, and this is the reason for the title 7 Minutes of Terror. You have 7 minutes, you need 7 minutes for the radio signal to be transmitted. So if something went wrong during the maneuver, there was no any possibility of a remote control. So you have to predict and anticipate any situation or all the situation you are able to predict. So at NASA, they used simulation, and in the simulation, they used a lot Adams in order to make, you see Adams here, to make this possible, okay? Let me show. This is a typical Adams model, and they use it for this kind of mission. So when the rover Mars surface, the first part of the mission was a success. Okay, so we have this situation. Okay, this is a success. Now, we have the rover on the Mars surface, and the rover has to perform some activity, like taking pictures or movies, or there is a robotic arm in order to get material or to make some operation, because you know this rover can help an astronaut when the humans when we be able to land on Mars. Again, this activity was performed using Adams at JPL laboratory. But this activity, as every other activity used in simulation, can be performed in academia, in university. So in all universities in Italy, we use Adams for thesis, also in La Sapienza. I can show you a lot of theses performed in the past years. In this activity, we have a group of students. They belong to a student team which participate to a European challenge called the European Rover Challenge, and they made a lot of projects. The first student create a simplified, from a geometrical point of view only, a rover model. When I say from geometrical point of view only, I mean that we have a very sophisticated suspension, very sophisticated transmission system in the chassis. Only the shape of the chassis is simplified, but the model is complex. And he was able to create a control system which allows the rover to move on any kind of surface. You see a lot of obstacles or a lot of problems on the road, but the rover was able to maintain the stability, so the camera is stable to make very nice pictures. The first student created this model from a numerical model using rigid wheels and rigid road. The second student introduced sophisticated geometry. From dynamic point of view, there is no any change in the result because it is only a nicer geometric representation, but the mass and inertia is the same. But the second student introduced the soft soil, so the algorithm for simulating the presence of sand, or in this case, the regolite, the surface of Mars. So we have wheels moving in a different road with respect to a rigid road. And the logic of the control was changed in order to consider also this problem. The third student introduced the flexibility of the road, the wheel, because you have an obstacle. You see here the complex transmission system made by gears, cams, links, shaft, etc. If you have a problem during the contact and there is no dissipation of energy, the force of contact is transmitted completely to this system, and this transmission system, you can have a failure in this complex and expensive system. So the wheel is flexible, so we have a Nastron representation of the wheel introduced in Adams. And then they create the prototype, the physical prototype of the rover. Then they started with the second rover with 6 wheels, not rigid, but with tires. And they repeat the same process: rigid road, obstacles, control system, validation of any kind of maneuver, introduction of flexibility of the components, introduction of irregularity of the road, evaluation of stress, displacement, vibration of the system, introduction of the soft soil. So we have different behavior in this front wheel, center wheel, rear wheel. Then they introduced the robotic arm of the robot for extraction of material, for object grasping. So we have a control system and the mechanical model of the robot. So they simulate and design also the logic of this and the grasping phenomena in order to make all this kind of operation, etc., etc., etc. Let me show. Imagine this kind of situation. It is not a movie. We have all the results, okay? So this is the important results. This is a belt mechanism in the transmission, in the suspension. And so they make the model more and more complex. Now we have a third release of this rover, and they attended the European challenge. This is an activity performed by a student in La Sapienza some years ago. Was a very great activity because she designed a new docking system. The docking system is a system able to make 2 different ships to enter in contact and to create one unique ship. Okay, so you have a contact between the chaser and the target. This is a simplified representation of the phenomena. We have the approaching model. We have the shaft here with the head. We have the need to enter in this drogue and to make the docking. So you have to attach 2 bodies together. We have a specific sequence for this docking maneuver. The initial, the capture of the shaft, the soft contact, and then the hard contact between elements. There is a control system able to measure from measurement of position, velocity, configuration, able to try to recover the right trajectory. So she modeled the full International Space Station with many bodies and many joints. And she modeled also the ATV, the approaching ship here. You see here some images. The system of logic is made in the following way. In Adams, we create the full mechanical model. In MATLAB Simulink, we create the control system. So we have the Adams model here, completely transferred in a superblock in Simulink. In Simulink, we evaluate, in Adams, we evaluate position, orientation, velocity, forces, angles, etc., etc. The logic manage this data, introduce some control, and then transfer back to Adams the movement for changing the roll, the pitch, the yaw, the longitudinal, lateral, to open the links, etc., etc. During this maneuver, even you don't have any disturbances, you can have 50 Newton of force in the contact. If you have some disturbances, so let me show you without disturbances. This is the movie. So here the navigation system control the maneuver. Now soft docking, opening some links here, and then retraction of the shaft, and you have the hard docking. You can find that if you have some disturbances in terms of position, velocity, etc., you can have a very higher value of contact forces. And this can be dangerous for the International Space Station. We have to avoid it. So she designed, let me skip some slides, she invented a new docking system. She introduced the flexibility of the shaft, and she created an equipment here able to reduce the contact forces during the contact. Let me show. This is the results. Even you have disturbances, the level of force is 1 order of magnitude less than before. How this system works? When you have this approach, now before the enter of this, you open some links, and it helps the soft docking and reduce also the hard docking phenomena. Okay, this is a typical thesis in which you have to design something new. But we have many other activity for satellite release or solar panel deployment, and we use Adams for making this kind of phenomena next time. We can simulate the centrifugal rotor. We can simulate mechanisms like this for the launcher of the rocket. We can simulate expandable or inflatable system like this. And you have hundreds of bodies, or you have bodies with control and flexibility. So we have other theses. And again, in La Sapienza, you can find other theses made in the past. Okay. So this is more or less the introduction of the technology and about the activity you can perform in aeronautical and spatial industry. There are any questions now?
Guys, go ahead. If you have any question, please ask.
In the first question, do you know which paths were assumed flexible?
Sorry, can you repeat?
In the docking mechanism, do we know which parts were assumed to be flexible?
The shaft. The shaft was made flexible. So this one, let me show. This part was flexible. Okay, instead of rigid body, it's flexible, so you can dissipate energy of contact because it can deform and adapt a little bit. Okay, it is not a rigid body.
Okay,
it's okay. Okay, you're welcome. Other questions? No questions? Okay. Please.
Is it all clear, guys?
Yep.
Okay.
Okay.
So now we can use the rest of time for introducing you a little bit the Adams environment. What I show you now is only an introduction of the environment. This will be introduced more tomorrow when we start with the satellite model. So do you, I guess that everybody of you has installed Adams Student Edition. As you know, Adams Student Edition is a complete release of Adams, which the limitation of the size of the model you can analyze. The limitation is the number of bodies, and the maximum number of bodies for the Student Edition is 20. The target of a Student Edition is not for use Adams for design or for thesis or for research, is only for making you more familiar with the code. It is for didactical purposes, okay? Università La Sapienza has full Adams installation for thesis and research. If you want to make advanced model as for a thesis, you can ask to use the Adams license in the lab in the department of La Sapienza. But you can ask to Professor Pasquale about it.
Yeah.
So, okay. Please. Hello?
Yeah, Daniele. Yeah, I was just confirming
that
anyone interested in having a thesis on this subject, we have the overall package available at DIMA. So, it's good.
Okay. So now, if you run Adams view, you see this first dialog box in which the first question is, do you want to create a new model or do you want to use an existing model? What is a model? The model is a multi-body system containing bodies, joints, forces, measures, design variables, script of analysis, etc. In a session, a working session, you can have at the same time many models. So a working session is not a multi-body model. A working session is only a working session. During a working session, you can create many models. You can perform 100, 1,000, 1 million analysis of different models. You can perform a post-processor on every model you want to use. You can merge different models, etc. So when I say you to save a working session, you don't save only the model, but all the activity you have performed in that session. Instead, when I ask you to save the model, you will save only the multi-body model without simulation, without results, without any, let me say, activity in terms of simulation and post-processor. When you create a new model, clicking this button, in this short course, we see only a very limited number of features of the code, and we will use a lot interactive features. It is a very limited capability. It's only because we have some hours, not days, for making the course. So we will use mouse, we will use buttons, icons, but you will see that you have access to a limited portion of the features. If you want to make you more and more familiar with the code, we have a lot of training material and you can improve your knowledge with my help or from yourself. So clicking with the left button of the mouse, new model, you open a new dialog box in which you have to fill to make something in this field. We can have requests for numbers, requests for strings, requests for options, or requests for file, directory, etc., etc. You can make your choices now, and you can change your choices in any moment. So it is only a starting window to make preliminary choices. For example, model name. If I want to create a model with two bodies, like a double pendulum, I write double underscore pendulum. The name is a sequence of alphabetical and or digit characters without space. Please forget to use space when you are working in a Windows environment, because the simulation tool doesn't, and principally on Windows 10, doesn't like the presence of space. So please avoid space in the names. Double pendulum, you can write in this way or you can change the name, but it is a sequence of characters. The second field is the gravity direction and value. Your mechanisms can work on Earth, space, Mars, whatever you want. You can decide to have the gravity on Earth, no gravity, or another value and direction of gravity. If we accept the default gravity on Earth, the gravity in this first window is directed along the vertical axis, negative direction, and the vertical axis you can see here is Y. This is only a preliminary definition of view. You can rotate and change the axis X, Y, Z, and you can decide to have gravity directed along Z, along X, or in another direction. This view in front of you is called front view, and it is a typical view used, for example, robotic industry. If you work in automotive or aircraft industry, the view is called the bottom view, and you have X horizontal, Z vertical, and Y entering in the screen. And every industry has its specific reference system. We can use the default now. The third question is the unit system. It's important to know, because the code has to solve differential, algebraic, and other kind of equation, it is important to know the units you are using for defining your parameters. We have many system of units. The international one, MKS, the international modified with a millimeter for length, the technical one, I don't want to use it, or the imperial, the British, I don't want to use it. Typically, we will use the modified MKS system with the millimeter, kilogram, Newton, second degrees. But every time you can change the units or assign to your parameter a different units. The code automatically updates the model. The last question is where I want to work, where I want to save my model, my results, my movies, my plot, my report, etc., etc. So the choice of the working directory is important. You can click on this icon, you navigate on your folders in your laptop, you select the working directory, and then you are ready to go ahead. We have 3 buttons here. If you click on OK, execute these commands, and the dialog box is closed. If we click on Apply, we execute these commands, but the dialog box is maintained open for making another operation of creation of another model. If we click on Cancel, we close the dialog box without execution. So please remember that you don't have to click on Apply and then OK, otherwise you create 2 models. Okay, so click on OK, and now we have the dialog, the window, the interface available. Some brief description. Menus here in the top. Using these menus, you have access to advanced features of the model. So we will use this menu. We don't use this menu. We use this menu only for some activities, but we have no time to use to learn all these commands. Instead, we will use a lot this icon here on the top and the icon here on the bottom, because they reduce our effort. It is a sort of click and go operation, very, very easy, very, very fast. As every fast operation, many intermediate steps are automatically performed. So you don't see the intermediate steps, but you accept that the code makes these steps for you. It is a very excellent way to start, but you have to accept some defaults from the code, okay? Or you have to modify the initial choices of the code. The next button here, bodies, connectors, motion, forces, simulation, results, allows you to access the modelization features for bodies, for joints, for forces, for elements, parametric analysis, advanced, super advanced features, etc., etc. We will use a lot this button. Our model will be created in this window in the geometrical characteristics, and the same data and other data will be also included here in the model browser. So we will have the access to the data of the model from the model browser here or from the graphical view. So let me start. What we have created till now: a model, double pendulum. If you expand bodies and forces, we see that when we have created the model, we have created automatically a body called ground. The ground is the universe. It is the scenario in which my system can move. So the universe, the space, the road, the room in a laboratory for a robot, etc. The ground is the fixed part. With respect, the code will write and will solve all the equations describing the model. The ground is the global reference system defined by X, Y, and Z, right and rule for orientation, and this body cannot be deleted, must always exist. If you delete the ground, you destroy the model. The ground can be defined also with some geometry in order to visualize, for example, the road or the walls of a lab, or if we need to visualize the scenario. For example, for our model of satellite, we don't need to visualize the sky, so we don't need any geometry for the ground. In the case of an aircraft, we need to have we can define the airport building, the road, etc., etc. Okay. This body has no mass because the mass is infinite and has no inertia. So you define the ground with the characteristic ground part. There is only one ground part in the model. The second element we have created is the gravity force. The gravity force is defined by this name, gravity, but you have also the gravity force displayed in the screen. But you can say me, I don't see the gravity force. There is a representation of it. Yes. In which way I can visualize it? Rotating the screen, for example. In which way I can rotate the screen? There are many ways. I show you a couple of them. The first way is on the top. There are some icons here to rotate, translate, and zoom views. So if you click at this icon and then you press the left button of the mouse, you can rotate the screen. And you can visualize the arrow which describe the gravity force, element and direction. If you want to translate the screen, you can click this icon and you can translate. If you want to zoom, click this other icon and you can zoom. If you want to zoom a specific region, click this icon, enlarge the region, and release the left button of the mouse. You can do the same with the keyboard. If you simply click the R Romeo, you activate rotation. If you click T Tango, you activate translation. If you click Z Zulu, you activate the zoom. If you click W Whiskey, you activate the enlargement of a region. If you want to restore the original front view, here you have discrete visualization. Clicking on this, you visualize the front view, or the right view, or the left view, or the bottom view, etc., etc. If you click on capital letter F, Fox, you restore the front view. Capital letter T, Tango, top view, etc. If you want to remember, if you want to visualize all these features, right button of the mouse, and here you see the keyboard command. These commands are also visualized, can be also, you can access to this command also here, and you can find many other commands, but again, we have no time to see all features. So, for example, I want to change the gravity force. I have two options. Can go with the mouse close to the icon, right button of the mouse, and I can modify, ask info, copy, measure, delete, rename, hide the gravity force. For example, modify, I can change the direction or the value. The same here. In the model browser, I go with the mouse here, right button of the mouse, and I activate the same feature. So now we want to create a double pendulum. We create a rigid body for the first pendulum. Click on bodies. We have rigid bodies with simplified geometrical representation, or flexible bodies, or some specific planar element, or we can have some advanced graphical operation. Let me start using rigid bodies. When you create rigid bodies, you have to define position in the space, orientation in the space, and inertia characteristics. This is what I did 30 years ago. Today, I can ask the code to make this operation for me, simply creating a geometry for this body. But I can create many geometry for a body. So remember, the geometry exists because the body exists. The body can exist without the geometrical representation. So I say this for the last time. Don't spend 1 second of your life wonderful geometry, because at the beginning of your design, you have no idea about the shape of your model. So spend your time instead in the important things like numerical evaluation of your analysis. Data, inertia, stiffness, damping, friction, etc. This is solids. I can click on this element. It is a link. I decide that the link belongs to a new body, and I put the origin of my link clicking a point on the screen, and then moving the mouse, I can decide orientation of this geometry and dimension of this geometry. When I click again, I create the body with the geometry and with the reference system in the model. You see here, reference system number 1, origin of the geometry. Reference system number 2, end of the geometry. Center of mass automatically positioned and oriented with it along the inertia, principal axis of inertia. If you go on the body, and click on modify, you can appreciate that Adams has created a body using this material, steel. The steel has this density. So this body has a mass of, in my model, 7 kilograms, and this moment of inertia calculated along this specific axis, X, Y, and Z, X, Y, and Z. If I want to change these parameters, I can change the material. So I can click on the material type field, right button of the mouse, browser, and I select another material, like aluminum. Then I apply aluminum. The density of the aluminum is 1/3 of the density of the steel. So now my mass will be more or less 2.5 kilograms. And consequently, the inertia. Or I can go on the geometry, link, modify, and for example, I can change the width of the link. Now the volume is increased. We have more material in the part. So now the inertia is 4.8 kilograms. If you don't like this way of evaluation of mass and inertia, you can make your choice, user input. So I can decide the stiffness, the mass and the inertia, my model. Now there is no more any relationship between geometry and material because we don't have material. We have user input data. So if I change the volume and I ask again the mass and inertia, the mass and inertia is not changed. But if I want to restore the geometry and material type method, select define mass way, select, for example, steel, and now this is mass and this is the inertia. I want that this body can move only in the plane. So it has 6 degrees of freedom. It can move horizontally, laterally, vertically. It can move rotating around itself, etc., etc. I want to connect connectors this body to the ground with a revolute joint. This is a revolute joint. The revolute joint allows only one rotation in a plane, removing 5 degrees of freedoms. 5 degrees of freedom. So when I click this, Adam asks me, which are the body you want to connect? I move the mouse on the screen, clicking the body. Then I move on the screen, clicking the second body. Then I move on the screen, clicking the location of the joint. And then the joint is created. With these icons, you can appreciate the type of the joint and the direction of the movement is outside of the screen. To run now a simulation, clicking this button, and you perform 3 seconds and time equal 3 of simulation with 300 steps, 300 steps of output. And you click on play, you will see the typical pendulum behavior. I can show you how the pendulum is moving. I can show you the volume occupied by the pendulum. We will repeat all these steps together in the next lesson, so don't worry, I repeat all the steps and I show you many other things, but only to give you the idea about what can do. And if you visualize the movement of this marker, this reference system at the end of the link, so if you create the measure of displacement, this point vertically along Y, you have this periodic behavior, typical of a pendulum. But now, if you click on bodies, you create another body with the link geometry. And you put the geometry here and orient the geometry in the way you want, like this. Now you have a double pendulum. If you connect with a revolute joint, the green body to the red body, in this point, we have two bodies and two joints, two bodies plus ground and two joints plus force. And now, if I repeat the simulation in which we have a double pendulum, you can appreciate that this is the first typical multi-body model, two bodies, two joints, one force, in which the behavior is absolutely impossible to predict analytically, because the system doesn't behave more as a periodic system. If I continue to run for other 3 seconds, you don't see the same behavior. And if I continue for other 3 seconds, you see, etc., etc. So, even if you have only two bodies, you are not more able to predict analytically the behavior of this system. You need to use numerical simulation. Next time, that is tomorrow, we will learn something about solar panel deployment problem, and we will create together this system of a satellite and a panel system in a very conceptual way, but believe me, you will see all the challenges and the difficulties a designer has to address in order to satisfy the requirements of this kind of design. Okay, so this is the last things for today from my side. There are a couple of minutes for questions if you have, and please, if you need to satisfy some doubts, please ask.
Any question? Okay.
How did you connect the two bodies? Because I tried to do this along with you, and I was not able to connect the two bodies, join the two bodies.
Okay, I show you again. Click on connectors, select the joint you want to use, for example, Revolut. Here you have to answer the question, which are the bodies you want to connect? Where is the connection point? Which is the orientation of the joint? So first body is the green body. I move on the screen till I see the name of the body and I click. Then I move on the screen selecting the second body. Then I select the connection, the point of connection, and that's all. If you click on modify, you can appreciate body number 3 and body number 2 are connected. If you make some mistake, probably you connect the body with the ground.
Yes.
And simply change the name of the body. Okay? You're welcome.
Okay, I think we are running out of time. So we thank again Dr. Catellani for our lessons. Again, tomorrow we're going to have the second lecture. All the material that Mr. Catellani will be showing in his lecture will be made available in the files on the Teams platform. So you will find everything there. So if there is no other question, I wish you a good day and we will see each other tomorrow. Okay. Bye, everyone.
Thank you. Bye-bye. See you tomorrow.